Hello, everyone. My name is Débora, and I'm a former master's student at Dalhousie University in Canada, where I did my research project on a wastewater treatment system in the Canadian Arctic under the supervision of Dr. Rob Jensen and Dr. Pernille. And together with Pernille and other co-authors, I also contributed with this work on the status of domestic wastewater treatment in the Arctic that I'm going to be presenting today. So this work was published in July this year. And as you can see, we have co-authors from all the Arctic countries, which is a super valuable, and that's actually what made it possible to provide such a comprehensive review on the status of domestic wastewater treatment in the Arctic. So to start, the status and also the challenges of wastewater treatment in the Arctic has actually received little attention in global inventories. So it is very hard to find information about the Arctic because public international databases, sometimes the Arctic data get lost in these informations because of the large nations with relatively small Arctic populations. So a lot was unknown. And when we have wastewater being discharged untreated or when treatment is deficient, we have the risk of environmental degradation and risks of exposure of local fauna and humans to chemical contaminants. And of course, we have all the challenges as well to address wastewater treatment in this context that is so particular and that has a lot of limitations and challenges. And what we identified as what we noticed is that usually the exchange of experiences and knowledges most frequently happens internally within the states and the countries, but infrequent exchange happens across the Arctic nations. So that's why this work was so important as a first stepping stone towards this framework of common understanding and knowledge exchange through this Pan-Arctic overview of current wastewater regulations and practices and wastewater loads discharged into the Arctic environment. So just very briefly mentioning our methods, we did a critical review. So we used a lot of public and official sources. We also retrieved a lot of information from scientific literature and also from personal communication and getting direct information from local authorities. So that's why it was so important to have co-authors from all the different regions. For the work, we also considered the AMAP area with some modifications to, for instance, in Sweden and in Russia, we had to include a little bit more than what would be included in the AMAP area just to be able to get statistical information. And to be able to get the loads, we consider both the local population within these areas, that is stated here, as well as the loads from cruise ships in the area. So jumping now into the wastewater regulations, I think the main thing that I would like to highlight here is how variable these regulations are across the Arctic. So for instance, in terms of the quality criteria, this can be based on effluent quality criteria in some places. In some regions, it is based on recipient-based, and in some regions, it is a combined approach. So considering both effluent quality and recipient-based criteria. The requirements, they are also defined sometimes by population size or they are site-specific. So most countries agree that a higher level of treatment is necessary for larger communities, whereas for smaller ones, maybe less strict requirements are required. However, the threshold triggering the size of the community, basically triggering the requirements for instance, to have a secondary treatment level or something like that is very different, ranging from over more than 100,000 people, for instance, in like Iceland, to less than 4 households in Alaska, for instance. So we also have a lot of differences. For instance, in Faroe Islands and in Greenland, wastewater treatment is currently not required, whereas in Russia, for instance, we have the strictest and most detailed regulatory criteria of all Arctic countries. We also have distinct standards or regulatory thresholds applied in Arctic or non-Arctic regions. So, for instance, in Canada, we have federal regulations that do not apply for the wastewater treatment systems located in 4 of the 5 Arctic regions in Canada. So usually the Arctic treatment systems, they have reduced requirements compared to the non-Arctic regions. And just briefly mentioning as well about the cruise ships and the sludge management. For the cruise ships, we have international agreements, mostly defining what is the distance to be able to, what is the distance from the nearest land that they can discharge untreated wastewater, and that we think that that's actually the most common practice, to discharge untreated wastewater in international waters. And for the sludge management, also it varies across the Arctic nations, but the most common practice is to dispose the sludge in landfill or use as landfill coverage. So now coming to the wastewater treatment technologies, we have a role of technologies that can be applied, and that's also true in the Arctic. And I'm gonna go back to these photos in a minute. So this map here shows us all the Arctic regions, and the pie charts here, they represent the percentage of treatment type technologies in each of the regions. The pie chart size also represents the size of the region. So larger pies represent larger communities with more population, and smaller ones represent smaller populations. And the colors here, they represent the treatment technology types. So for instance, the light brown here represents no treatment. The green one represents centralized natural treatments, dark blue, centralized conventional treatment, light blue on-site, and red is unreported or unknown. And I'm going to show examples of all the systems in a minute. So the first thing that we can notice is that the treatment types, they vary a lot across the Arctic region. Here, 59% of the wastewater in the Arctic is treated by centralized conventional types of systems, which can range from preliminary screening to advanced or tertiary treatment. And these types of systems, they are most common in larger communities, especially in the Scandinavian region here, especially in the Scandinavian Arctic, Russia, Iceland, and urban Alaska. So here are just some examples so you can see how that looks like. These systems are located here in Finland and in Norway. So you can already imagine also how hard it is to make those things operate well in many contexts in the Arctic. 5% of the wastewater is treated in centralized natural types of systems, which includes ponds, lagoons, wetlands, and infiltration systems. And this is used mostly, especially in North America. In Canada, in the Canadian Arctic here, it is the type of system used to treat more than 85% of the wastewater generated in the region, and is also common in some regions of Alaska. And here are some examples. This first photo here is actually where I did my research project in the Northwest Territories in Fort Good Hope, where they have this infiltration kind of system. And here's another example of those type of natural or passive wastewater treatment systems in Nunavut. So 60% is treated on-site, and this includes septic tanks and sometimes small package plants. And this is the most common type of treatment in rural areas of the Arctic region, and especially here in the Faroe Islands, where almost 100% of the wastewater is treated by this type of systems, septic tanks. So here are some nice examples this one here is in the Faroe Islands that Rakul sent me. So that's a very nice photo where you can see the inside as well of the septic tank and how that looks like from outside. So this one, for instance, is for more than 800 people, and then we also have the small package plants to treat wastewater for just one household in this example from Finland. So this leaves us with 14 to 20% of wastewater being untreated or unknown. So when we compared, so for instance, also in Greenland, I forgot to mention here that no wastewater is treated. So you can see here that all wastewater in Greenland has no treatment at all. So when we compare this number here, this percentage here, with the global situation, where it is estimated that 48% of the wastewater is untreated, it seems that the Arctic region is ahead of the overall global situation. However, what we notice and what we're going to be discussing later is that the systems, they frequently fail to meet the regulatory criteria, or they have reduced requirements as well. So the levels of treatment is likely significantly lower, as we are going to discuss next. So here are just some examples of situations where there's no treatment in Greenland, these ones. So both in bigger towns, such as Sisimiut here, as well as in smaller places, such as Itlag, where they use this type of bucket toilets, which is basically a dry toilet with plastic bags. Okay, so another thing that we can get from this map is that the wastewater emissions, they are not uniformly spatially distributed throughout the Arctic. So we have a combined population in the region here of 5.2 million inhabitants. However, as we can see, is located in the Arctic Russia, followed by 23% in northern Norway. And in Greenland, for instance, where we have no treatment at all, we only have 1% of the Arctic population living there. And the same thing happens with the cruise ships, where most of the wastewater is discharged without treatment. However, it only represents as well 1% of the Arctic population. So we can see that the majority of the wastewater load is actually discharged in this southeastern area of the IMAP area, which includes here the northern Norway, Sweden, and this part of Russia. And the majority of the untreated wastewater originates in the Arctic Russia. So now coming to the wastewater treatment levels, just briefly mentioning here what we consider to be these levels of treatment. We can range from preliminary treatment, where we have basically the removal of larger particles via screening. We can have primary treatment, where we add a sedimentation step, and we can remove some suspended solids and some organic matter as well. Then when we add more biological treatment here, we can have a secondary treatment level, where we can remove more biodegradable components. And as we add more steps here, we reach tertiary levels, usually focusing on enhancing nutrient removal and enhancing disinfection as well. So here is the map again, but now showing the pie charts. Now they show the level of treatment in all the regions. So the brown here again represents the no treatment, or where treatment is unknown. And as we get darker here in the blue color, we increase the level of treatment from preliminary to tertiary treatment. And what we can notice here is that in terms of treatment levels, the Arctic regions is lacking behind when we compare to Europe and North America, for instance. So the majority of the wastewater is treated to a preliminary or a primary treatment level, and we only have 19% of wastewater being treated to a secondary level of above. And when we compare this with the estimates from Europe and North America, where 86% is treated to at least a secondary level, we see that the Arctic is really lacking behind on that. So just talking again about the ecosystem impacts, right? When we have discharge of wastewater not treated or not completely treated, we have these risks of environmental degradation or exposure to contaminants. However, we have only a few studies developed on evaluating these ecosystem impacts in the Arctic. So we found some studies in Canada, mostly in Canada, and also in other regions. And what these studies show us is that the ecological effects, they are measurable. However, they are localized, and often they are focused on, they are described for larger communities of above 2,000 inhabitants, for instance. There is also indications that the wastewater is a potential source of antibiotic resistance, but natural sources can also play a role. So we still need more work and more studies related to that to be able to really understand what are these ecosystem impacts. And just highlighting here that there are efforts as well to develop and design solutions and innovations related to wastewater treatment in the Arctic. So for instance, there are research projects on developing specific guidelines for designing systems in the Arctic. For instance, my master's project has a component on that as well, so trying to understand what are the specific considerations that we need to include when we are designing systems for the Arctic. There are still a lot of challenges related to monitor those systems in decentralized, remote, and small-scale treatment systems. So, for instance, as you can imagine, it's very hard to collect representative samples. There are logistical challenges, and so on. There are lab and scale efforts being developed to try to improve and understand the mechanisms or the performance of those systems in the Arctic. However, most of it has not been yet scaled up. And there are discussions and technologies advances happening as well. So highlighting, for instance, the Alaskan Water and Sewer Challenge that is focused on developing improvements for the honey bucket users. For instance, here also I'm using a photo from a thematic network summer school that happened in Greenland in 2023 that I was able to participate as well, where we gather a lot of people to discuss these design solutions and innovations for treatment systems in the Arctic, but it's still a big challenge. And just to conclude here, what we found what I would like to highlight here is that the wastewater regulations, the treatment technologies and treatment levels, they are highly variable across the Arctic region. We found that 14 to 20% is untreated, but these emissions are not uniformly spatially distributed throughout the Arctic. As I mentioned before, they're really more, the emissions happens more in a specific region in the southeastern area of the AMET. Less than 19% of the wastewater treatment active secondary treatment level, which is significantly lower than the global regions with the high service levels. And that's due to reduced requirements and also challenges to make those the systems operate and perform well. And we have a lot of recommendations. So I'm just going to highlight some of them here. First is the need to develop methods to monitor and evaluate ecosystem impacts of wastewater in the Arctic. As I mentioned, there's just a few studies on that. Maybe the main one here is to keep establishing and enhancing this framework for collaboration on wastewater across the Arctic nations. As we see, many of the challenges are related to the particularities of the Arctic, the climate conditions, and so on. So importing solutions from the south is really not a good idea. So there's really this need to knowledge exchange. And another recommendation would be to assess the wastewater as a source of anthropogenic chemicals, which is going to be a good link to the next presentation that Pernille is going to give us on that. So with that, I finished my presentation and thank you very much. And now I'll hand over to Pernille that's going to give us a nice presentation as well. So thank you very much.
Thank you very much, Débora, for the nicely providing the background for this next presentation. My name is Pernille Erland Jensen, and I'm an associate professor at the Technical University of Denmark, My primary educational and research activities are affiliated to the university's campus in Sisimiut, Greenland, and centered around Arctic communities and their environment. I will present results of an ongoing study review work that we are doing on the importance of wastewater as a local source of POPs and chemicals of emerging Arctic concern in the Arctic environment here. So our goal with this work is to contribute a piece to the puzzle to evaluate the importance of local sources in contrast to long-range environmental transport of chemicals to the Arctic region by evaluating the importance of wastewater. And to be able to do that, we needed to understand not only the load and treatment level of wastewater in the Arctic, but also to know what has been monitored in the Arctic concerning the concentration and the fate of POPs and CACs in wastewater discharge in the Arctic. We wanted to know whether POPs and CACs from Arctic wastewater give rise to increased concentrations in the local environment that could risk exposure to local biota and humans, and then to find out whether we have any remaining gaps of knowledge. And to do all of this, we made an in-depth literature review. We identified first a number of factors suggesting that the content of POPs and CACs in Arctic wastewater is likely to be different from wastewater in other regions of the world. First, there is the overall treatment level presented by Débora, which is lower. And second, the domestic water consumption in the Arctic region tends to be smaller in remote Arctic communities compared to more populated areas, due in part to lack of water and in part to lack of piping. And third, the infiltration of groundwater and surface runoffs into Arctic sewer systems is less likely due to the lack of sewers or sewers being placed above ground due to permafrost, or due to no or limited groundwater flow due to permafrost, due to less extensive sewer networks because of the small communities, and due to separate surface water that runs off in ditches in many Arctic communities. All of this could potentially lead to higher concentrations of chemicals in wastewater in the Arctic region. On the other hand, the absence of significant industrial production and a presumable less abundant consumption of modern convenience products such as PPCPs in rural Arctic communities might lead to lower concentrations of micropollutants in Arctic wastewater compared to non-Arctic regions. And distinctive for the Faroe Islands and Iceland, these countries have a very high water consumption per capita in contrast to the rest of the Arctic. So really, it's impossible for us to guess what the concentrations of these chemicals would be in Arctic wastewater. So we looked into literature, and although more than 10,000 studies have been published worldwide in the past 2 decades about POPs and CACs in municipal wastewater, and quite a few reviews have been written, no Arctic studies had been included in any of the reviews we could find. This, however, does not mean that Arctic studies do not exist, though they were pretty few. We found 32 sources reporting on relevant chemicals in Arctic wastewater. But these studies, however, are unevenly distributed over the region. Most data was found from Canada and the Scandinavian countries. So definitely there is a gap of knowledge to understand what the contribution is from the rest of the region. Only 2 wastewater treatment plants have been studied in Alaska, and no data are available from wastewater treatment plants in the AMAP region of neither Russia nor Sweden. Based on the available data, we calculated country-specific 75th percentiles for untreated and treated effluents in the Arctic. And we set this information in relation to minimum and maximum concentrations observed in non-Arctic wastewater treatment systems, according to 12 global reviews and 8 comprehensive national investigations. So here we have the same schematic conventional wastewater treatment plant as Débora showed earlier, with the preliminary, primary, secondary, and tertiary treatment steps. Such systems are by default not designed to remove anthropogenic chemical substances such as POPs and CEACs. However, in wastewater treatment systems, applying treatment at secondary level or above, easily degradable organic or volatile chemicals are largely removed by biodegradation or volatilization, as shown here in red. And hydrophobic pollutants, such as most of the legacy and new POPs and some of the CEACs, are also supposedly predominantly removed mainly via absorption to particulate organic matter, such as biosolids in the activated sludge process of secondary treatment. Generally, more than 70% of these compounds are expected to be removed. But poorly to moderately biodegradable hydrophilic pollutants, such as many of the PPCPs, pesticides, and household chemicals, including corrosion inhibitors, sweeteners, chelating agents, and phosphorus flame retardants, are not expected to be removed by conventional treatment, even at tertiary level. Quaternary treatment is needed, such as advanced oxidation processes, activated carbon filters, or membrane-based technologies to remove this type of contaminants. And requirements for treatment for such types of chemicals has only just come forward with the recent new EU wastewater directive, and only in the EU countries apart from Switzerland, where it has been in place for a while. So these current advanced technologies for quaternary treatment are only efficient if tertiary treatment level has been reached before implementing this. And as we know, this is true for only 3% of Arctic wastewater. It is unlikely that these contaminants will be treated in Arctic wastewater in any nearby future. The full list of contaminants included in our search was long, including all POPs and CEACs listed here. And I will now show which of those were analyzed in Arctic wastewater here with the colors. Now I show with green the PFASs and the PPCPs, which are the target contaminants that had been analyzed in most samples and most different locations in the Arctic region. At least 20 different samples had been analyzed of these compounds. But for the legacy POPs, apart from heptachlor and toxaphene, the compounds were analyzed only at 1 to 3 different instances. We had two studies from Finland and one from Iceland showing data for these compounds. And we had no analytical results for these compounds in untreated Arctic effluents, so only in treated Arctic effluents. So very little is known on the legacy POPs in wastewater in the Arctic. And what we can say is that in all 3 studies, all the compounds monitored in the Arctic effluents were found to be below the detection limit of the study. This is in contrast to the non-Arctic studies, where the concentrations of several of the legacy POPs after secondary treatment were observed at concentrations 2 more orders of magnitude or more higher than the detection limit of the Arctic studies. So this indicates that there is a higher presence of these compounds in wastewater in more southern regions, but of course based on a relatively low number of samples. Among the new POPs, most PBDEs and PFASs were measured at 9 to 37 occasions in Arctic wastewater, and most of these compounds were also documented to be present in Arctic effluents. But many other new POPs, those marked with red here, have, to our knowledge, never been analyzed in Arctic wastewater. And the POPs marked with yellow here have been analyzed only at 1 to 3 occasions, similarly to most of the legacy POPs. And also, similarly to most of the legacy POPs, they were all, apart from hexabromocyclodecane, found to be below the detection limit of the studies. Among the CEACs, microplastics, most phenols, PAHs, and a variety of PPCPs and phthalates have been analyzed on several occasions and locations in Arctic wastewater. The siloxanes, in contrast, have been analyzed only on 1 occasion in Arctic wastewater, and no observations were found for the remainder of the CEACs, including organophosphate esters, apart from TBP, which was analyzed in 1 occasion in Arctic wastewater. Among all the CEAC groups analyzed, the concentrations observed were highly variable, from below detection limits for some of the phenols and PAHs to concentrations that were 10 to 10,000 times higher than the detection limits for others. All the PPCPs that have been analyzed at more than 1 occasion were observed above the detection limit. Those are the ones marked with green here. But although many PPCPs were among the most extensively monitored compounds, only 5 of the 13 indicator pharmaceuticals listed for future monitoring and regulation in the EU have ever been analyzed in Arctic wastewater. Thus, here is also a significant gap of knowledge with the red marked substances here that have never been analyzed in Arctic wastewater. I have selected 4 different micropollutants groups among the most studies as examples of our results for this presentation. This figure shows the country-specific 75th percentiles of BDE 47 and 99. These PBDEs concentrations were studied at wastewater treatment plants in Canada, Finland, and Iceland, as you can see on the x-axis. The yellow bars show the 75th percentile concentrations of untreated wastewater, while the green bar shows concentrations after nature-based treatment, and the dark blue after secondary or tertiary treatment, and the light blue after primary or preliminary treatment. The red bar shows the concentration range in treated non-Arctic wastewater, irrespective of treatment level. And please note the logarithmic y-axis on these figures. The maximum concentration in untreated non-Arctic wastewater was at least 3 times higher compared to the 75th percentiles in Arctic wastewater treatment plants. But with only 2 observations of untreated Arctic wastewater that differ in concentrations by almost 2 size orders, no general conclusions can be drawn on differences in PBDE concentrations between Arctic and non-Arctic wastewater. The 75th percentile concentrations of both compounds were only slightly lower in treated compared to untreated wastewater in Canada, where nature-based systems was used, and comparable to the maximum concentrations in treated non-Arctic systems, indicating that pond treatment in Arctic climate may not be efficient for removal of PBD compounds. The conventional secondary and tertiary treatment plants in Finland, in contrast, resulted in a significant reduction in concentrations of 5 to 10 times. Like legacy POPs, PBDs tend to partition to solids during wastewater treatment, which is likely to explain this reduction of PBDs in water observed during conventional secondary or higher treatment. This figure shows similar data for PFASs. The illustrated PFASs were studied in wastewater from Canada, the Faroe Islands, Finland, Greenland, Iceland, and Norway. In general, within each country, the concentrations of these PFASs were identical to or higher in treated compared to untreated wastewater. And this has been observed previously elsewhere and is likely due to the transformation of unmeasured precursors to the target analytes during wastewater treatment. The Faroe Islands was the only country where PFAS was analyzed at two different treatment levels, primary and secondary. In this country, the 75th percentiles of 3 of the compounds were higher after secondary compared to primary treatment, confirming the hypothesis about transformation during biological treatment. The maximum concentrations of PFAS observed in non-Arctic wastewater, both treated and untreated, were between 1 and 3 orders of magnitude higher than the 75th percentile concentrations in Arctic wastewater, indicating a lower average concentration in Arctic wastewater compared to globally. Analytical values of the 3 polycyclic aromatic hydrocarbons, naphthalene, phenanthine, and benzapyrene in Arctic wastewater are presented here as representatives of this class of chemicals. PAHs were studied at Arctic wastewater treatment plants in the Faroe Islands, in Finland, in Greenland, in Iceland, and in Norway. In general, the concentrations in Arctic wastewater was in the lower range of non-Arctic studies, but interestingly, the Greenlandic phenanthine concentration exceeded even the maximum concentration ever observed in non-Arctic studies. The concentrations of PAHs were comparable across treatment levels in the Arctic studies, indicating little impact of treatment, though some reduction is indicated in the Finnish effluent from tertiary treatment and in the Faroese secondary treatment for naphthalene and phenanthine. And finally, we have some examples of the PBCPs here in this figure, where we have chosen ibuprofen, naproxen, metoprolol, and atenolol as examples. These PBCPs were studied at Arctic wastewater treatment plants in Alaska, Canada, the Faroe Islands, Finland, Greenland, Iceland, and Norway. The maximum concentrations in treated and untreated wastewater collected from non-Arctic wastewater treatment plants were significantly greater than the 75th concentrations in Arctic wastewater treatment plants, indicating a lower consumption in the Arctic of medical compounds. In general, the concentrations of PBCPs in Arctic systems were comparable across wastewater treatment levels, though again, the conventional treatment in the Finnish plant with tertiary treatment showed more than 99% reduction of ibuprofen, and a primary treatment plant in Norway showed a 2 to 3 times reduction also of ibuprofen. In contrast, the concentrations of both naproxen, metoprolol, and atenolol were reduced by 80 to 87% by the pond treatment system investigated in Canada. So here, the pond treatment system showed to be actually more efficient than the conventional mechanical plants. The results collected here suggest that high treatment levels are necessary to reach efficient elimination of PBCPs, and supports the finding that the removal of PBCPs is slower in Arctic compared to non-Arctic wastewater treatment plants, possibly due to the cold temperature and reduced biological activity. We also chose microplastics as an example. Microplastics are relevant as CEACs due to the long list of chemicals they carry, either as their intended functional additives or due to non-intended adsorption during usage and environmental exposure. It is widely recognized that the number of microplastic items in environmental samples increased with the decreasing particle size, and therefore it's inherently difficult to compare results of investigations with different cutoff sizes in the lower end. In this figure, we have separated the results accordingly, with studies sampling down to 20 micrometer or less shown to the left, and studies sampling down to 250 micrometer or higher shown to the right. The data indicates that the microplastic concentration is significantly lower in Arctic wastewater compared to non-Arctic when it's not treated. And the tertiary treatment in Ny-Ålesund also was shown to be really efficient in decreasing the microplastic particles with several size orders. But preliminary and primary treatments, as shown in Iceland to the right, did not result in any removal of microplastics whatsoever. This may in part be due to the very dilute wastewater in Iceland, which can be more difficult to treat. An estimate of the annual load of the most frequently monitored POPs and CACs was calculated. Altogether, the load of the 20 compounds most often evaluated summed up to 5.2 tons per year from wastewater in the Arctic. And 46% of this comes from the 20% of the wastewater which is discharged untreated. The load ranges from 5 grams per year of benzapyrene to 1,460 kilos per year of DINP. The combined load of the most abundant chemicals, DINP, DEHP, and ibuprofen, constituted 79% of the total mass load of the monitored chemical to the Arctic environment. A number of studies have provided evidence that domestic wastewater is important as a local source of contaminants in the Arctic. And we selected 2 examples here to show how concentrations of these contaminants are higher in the vicinity of wastewater discharges. This figure shows PCB, PAH, and benzapyrene concentrations in sediments in the harbors of Hammerfest in Norway and Sisimiut in Greenland compared to the OSPAR background concentrations. And what we can see here is clearly that the concentrations are higher at the H4 site in Hammerfest, and this is the only site where domestic wastewater is discharged, while all the other sites are impacted primarily by industrial harbor activities. So this suggests that domestic wastewater is a significant source of this kind of contaminants. And here we have another example, which is microplastics from the fjords of Nuuk, the capital of Greenland. And here it's clear that the concentrations of microplastics are higher at the sites 4, 5, and 6, which are downstream for Nuuk, while sites 1 to 3 lie upstream. And this suggests that microplastics origin from Nuuk and likely to primarily origin from the discharge of untreated wastewater. But of course, we cannot know that for sure. We looked a bit at industrial wastewater also, but the environmental burden of industrial wastewater is not generally publicly very easily accessible. It typically remains as internal and often confidential knowledge between industry and approving authorities. An indication of the type of chemicals of Arctic industrial wastewater can, however, be obtained by observation of the predominant industries. And the Arctic region and its subregions rely economically on relatively few major industrial sectors, including mining, refining, fishery, forestry, agriculture, defense, and offshore industries. The listed industries are variably presented across the region, and the figure below the text here shows how almost all industrial wastewater comes from fisheries and heat exchange in Iceland, while fisheries and service and trade sector are more important in Greenland. What we can also see from this figure is the previously mentioned very big difference in the water consumption in general among those two countries. Anthropogenic contaminants are not typically connected to wastewater from food production, apart from cleaning agents consumed for hygienic purposes during production. On the other hand, a wide range of pharmaceuticals have been closely related to aquaculture, including antibiotics, disinfectants, and antihelminth drugs, which are used in aquaculture activities for disease control. However, most of the available information on this is from Asia, where 90% of the global aquaculture takes place, and where the situation is not necessarily comparable to that in Norway and Faroe Islands that also have aquaculture. For example, in Norway, due to strict regulatory oversight of the use of pharmaceutical drugs, aquaculture has been able to reduce its total consumption of antibiotics by more than 99% between 1995 and 2019. And in the Faroe Islands, antibiotics have not been used in salmon farming since 2004. The oil and gas industry produces wastewater streams comprising drilling additives. The environmental toxicity and persistence of drilling chemicals can vary significantly, and the choice of chemicals used is typically a compromise between process stability and environmental safety, and subject to approval by authorities. Among the listed target POPs and CAC compounds, PFASs are extensively used as oil field production chemicals and aqueous film-forming foams in oil fields, and also phenols are found in wastewaters of petroleum industry and oil refining industry. PAHs occur naturally in crude oil and gasoline and are in addition produced when oil and gas are burned, and might thus also be present in oil and gas industry wastewaters. Mine waters are primarily connected to environmental contamination by acid mine drainage, heavy metals, and radioactive elements. But a long range of organic chemicals are also frequently used in mineral processing, including PFASs, which have long been used as part of both processing through inclusion in surfactants or floating processes and other performance chemicals, such as hydraulic fluids and fuel additives, and in firefighting activities. The figure to the right here illustrates how PFOA has been observed in recipient waters at elevated concentrations in the vicinity of mining sites in the subarctic Canada. But it hasn't been easy for us to find many studies with this kind of evidence for the Arctic region. Débora mentioned sludge, which is very variable due to the variable and often rudimentary wastewater treatment in the Arctic region. And therefore, the sludge quality also is very variable. The substances that have been detected in sludge samples from the AMAP region include pharmaceuticals, PFASs, phenolic substances, siloxanes, and organic phosphorus compounds. However, the number of investigated samples in the studies was very small, and the available data is from Faroe Islands, Iceland, and Greenland only. Overall, sewage sludge in the AMAP region is confirmed to be a sink for organic micropollutants, but the assessment of risks related to placing this sludge in Arctic aquatic environments and also terrestrial environments is difficult due to the lack of toxicity data for relevant organisms. Organic pollutants can potentially remain for long times in the Arctic environment, and one study showed that after 4 to 6 months of outdoor storage, concentrations of organophosphate esters in sludge remain stable, suggesting that these compounds are not easily degraded in sludge in the Arctic environment. And finally, we found a bit of data on urban runoffs, which also can contain a variety of POPs and CACs. The available studies focused on trace organic contaminants in stormwater in Arctic communities. They are sparse, but they have demonstrated the relevance of urban runoffs as a source of POPs. Several triazole compounds were detected in snowmelt runoff from urban landscapes and snow storage facilities in Anchorage in Alaska at concentrations comparable to those reported in non-Arctic regions. And it also showed that pulse loads to recipients occurred during initial snow melt, as shown in this figure. In conclusion, data on target compounds are available from Arctic wastewater treatment systems, but the region is unevenly represented. Chemicals that are currently discharged with wastewater in the Arctic region can be expected to continue to be discharged also in the future. Legacy POPs concentrations appear to be lower in Arctic treated wastewater compared to non-Arctic, but only few observations have been made, and no information about legacy POPs in untreated Arctic effluents could be found. Some compounds are found in Arctic wastewater at concentrations equivalent to global observations, but others are found at lower concentrations. Low impacts of Arctic treatment systems is observed on many POP and CAC compounds, but higher treatment levels seem to improve the removal also in the Arctic. Phthalates and ibuprofen constitute the biggest mass of POP and CAC chemicals discharged by wastewater in the Arctic among the 20 most well-documented chemicals. There is evidence that local wastewater discharge of different CAC chemicals increases the environmental concentration locally at a scale between tens of meters to tens of kilometers. Very little is known about the treatment and discharge of industrial wastewater. In particular, wastewater from oil, gas, and mining industry is likely to contain organic chemicals such as PFASs. And urban runoff is likely to contain chemicals related to road, buildings, and vehicles, materials, and usage, and that they are also discharged to the environment. And that was the end of the presentation. Thank you very much for listening.